Okay, so hello everyone. Welcome back to Bangalore Theory Seminar Series. Today we have Jaykrishnan as a speaker. Jaykrishnan is a PhD student at Technion, where he is advised by Professor Asaf Levin. He has mainly worked on scheduling and bin packing with cardinality constraint during his PhD, and he has also dabbled into robust optimization of water quality and some deep learning projects. So today he'll be talking about scheduling with cardinality dependent unavailability. So with this, I hand it over to Jaykrishnan.
Thank you for the introduction. So, as was said, this work is jointly with my advisor Asaf Levin. So today the talk will be about some introduction to approximation schemes, and then to the main problem, which is scheduling with cardinality dependent unavailability. So I'll start. So first I'll give some introduction on the what a scheme is, and then I'll try to give some framework for developing approximation schemes, which is a very basic overview of the techniques. And then I'll go into the problem definition, and then I'll go into the scheme of the problem. So to start with, an approximation scheme is basically a family of approximation algorithms. A polynomial time approximation scheme is a family of approximation algorithms such that for every epsilon, we have a 1 plus epsilon polynomial time approximation algorithm. And an FP-task is basically a p-task where the time complexity is polynomial in the input encoding length as well as 1 over epsilon. So for approximation scheme, the epsilon is not part of the input. We give epsilon to the scheme as a measure of how close you want the solution to be. And these are like the absolute approximation algorithms and schemes. Next, we go into the asymptotic approximation schemes. So here it's a little bit different. So here the approximation ratio is asymptotic approximation ratio, and it's defined as the smallest r such that the cost of the output of the algorithm is at most r times the cost of the optimal solution of the problem plus a constant. Now the constant here will be independent of the input, but it can be a function of 1 over epsilon. So that is the absolute asymptotic ratio. Now, based on this, we can redefine the betas and AF betas. A betas is corresponding to the betas is a family of approximation algorithms, such that for every epsilon, we have a approximation algorithm of asymptotic approximation ratio equal to 1 plus epsilon. And similarly, then we have an AF betas where we have the extra requirement that the time complexity is a polynomial not only in the input encoding length, but also in 1 over epsilon. So that's like a general introduction. So here I just show some examples of the time complexity and the cost bound. So for a polynomial time approximation scheme, we have a time complexity that is proportional to the something like this. So we have it's a polynomial in the input encoding length, but it's not polynomial in the 1 over epsilon. And for an FP task, we need to have a time complexity that is polynomial in both input encoding length as well as 1 over epsilon. And the cost bound are the absolute performance ratios. And then when we come to the asymptotic variance, we have time complexity like very similar to the p-task and FP-task. So it should be polynomial in the input encoding length. And it should, in case of FP-task, it should be polynomial in both the input encoding length as well as 1 over epsilon. And the cost bound here is different. We have the absolute approximation ratio. So here we can have an extra constant. And this constant can be a function of epsilon or not a function of epsilon. So in this case, all the integers are just representative, and they can be any other values. So this is the main class variations between the betas and the asymptotic variations of them. And then I'll just try to explain some techniques that I have used in developing approximation schemes. So when we consider an algorithm, this is the basic schematic of an algorithm that we usually see. So we have an instance that is input to the algorithm, and then the algorithm takes in the input instance and produces an output. So now these are the main three components: the instance, the algorithm, and the output. Now, when the problem that the algorithm is trying to solve is NP hard, assume that the algorithm is an exact algorithm. Then, and if the problem is NP hard, then the algorithm A would be very slow. And so we need to somehow speed up the algorithm. Now, speeding up, it means that we will lose some accuracy in the results, but we can speed up the running time of the algorithm. So there are three ways to do this corresponding to each of these components. So the first component is, first technique is to add structure to the instance that is input into the algorithm. And then we can add structure to the execution of the algorithm. And then we can add structure to the output. I'll explain the adding structure to the instance and adding structure to the output part today. By explain, I'll mean like a general overview because it's very problem specific. This structure is a very loose term and it's very problem specific. So to start with, this is the like the general methodology for adding structure to the input is essentially we transform this input instance into a rounded instance. So here we have this like very um, we have an input instance that doesn't have much order, and it's very hard to find a solution for this directly. So what we do is we convert this instance into a different instance. So thereby we lose some accuracy of the results. But then this new instance, this I hash, will have some structure that we can exploit that makes us allow us to solve this problem quicker. And then we solve this I hash, and then we get an optimal solution for that. And then once we have this optimal solution, we transform it back to an approximate solution for the original problem. So that is the basic technique of adding structure to the input. As I said before, this structure is very loose term. It depends very much on the problem, and the rounding also is very problem specific. So the next, so I'll just give an example here. So the top schedule is just a schedule of on a single machine. Like we have these jobs. The gray ones are like jobs that have very small size, relatively small size compared to the other jobs, and they are called small. And the white jobs are large. So what we can do is we can just combine all these gray jobs together and to make a one block of a job. And what we get is that the number of distinct item sizes in the input instance can be reduced significantly. So if we have that this size of a job is at most epsilon types the makespan. Oh, sorry. If we have that, sorry, I can't write. It's like if we have the size of a block is at least epsilon times the makespan, then the number of jobs on a machine will be at most 1 over epsilon. And then we can enumerate the possible ways to pack these jobs, I mean, in the rounded instance. So that is one example of rounding. Then another example is when we use geometric rounding of the sizes of the jobs. So essentially we round up the sizes of the jobs to an integer power of 1 plus epsilon or some other number. And then we can get like more structure to the instance. And another famous rounding technique is the linear grouping and rounding in bin packing, which I think almost everyone is familiar with. And then another technique to create approximation scheme is by adding structure to the output. So in this case, we partition the feasible region, the output space of an instance into many different districts. So each district here is each of these is a partition, and the partitions are made in such a way that like there is some property that is common between all the solutions in a partition. And so then we can then use this property in a district and exploit that and solve the problem for that particular district quickly. And then we get an approximate solution for those different individual partitions. And once we have the individual solutions, we can just choose the best among them and output that as the part of the scheme. So that is adding structure to the output. So an example of this is when we are, again, I'll give a scheduling example. So assume we have like two machines scheduling with makespan minimization. And then what we can do is we can we can define a district based on the scheduling of the large jobs. So if a large job is of size at least epsilon times Cmax, where Cmax is the makespan, then the number of packing scheduling of the large jobs is we can enumerate those. And then once we have the packing scheduling of the large jobs, we can then schedule the small jobs in easily. And the scheduling, adding small jobs back to the machines, it's can be done in a very cost effective manner. We need to only increase the makespan by epsilon times the makespan. So this is one example of how to add structure to the output. So just to give a summary of these two techniques, so we can add a structure to the input instance by simplifying it, and the simplification will enable us to find near optimal solutions quickly with respect to the rounded instance. And adding structure to the output by partitioning the feasible region allows us to utilize some properties inside this solution space in each of the partitions to quickly find a close enough solution. So those are the two techniques that I'm most familiar with. So I explain those. So now we'll get into the problem. So the problem is that this is a scheduling problem, and in this problem we have machines that are not continuously available. So after processing a fixed number of jobs, the machine becomes unavailable. So basically, after processing a fixed number of jobs, we need to add idle time in the machine. And once the idle time ends, it can restart again and start processing the jobs. So we consider the makespan minimization variant of the problem. So this is the term called the unavailability requirement. It's basically, we introduce it basically to for ease of use. So it just means that after processing k jobs, the machine becomes idle for a time period u. So in the top here we can see that this is a schedule. This schedule is like the normal schedule when the jobs are continuously processed, and we can, so it finishes much faster. But in this case, when unavailability requirement is introduced, like the bottom instance, what happens is that after processing like k jobs, here k is equal to 2. So after processing k jobs, we need to add idle time. The light blue region, light blue job is an idle time job. So after processing two jobs, we need to add idle time. So again, after processing two jobs, we need to add idle time, and this repeats. So the makespan is increased, and the original solution that is feasible for the original scheduling problem with makespan minimization is not feasible for this problem. So then based on this, now we have like two variants. So when we consider that the scheduling problem has a fixed due date, then we need to then we need to process all the jobs within before that due date, and then we get a bin packing variant. So here we have many machines that are available to us, but we have a fixed due date. So it's essentially equivalent to a bin packing scenario. And when we have a fixed number of machines and we don't have a restriction on the due date, it's a scheduling variant. So I'll give just a comparison of these two. So first we have the input instance to the scheduling variant. So the input instance is the number of jobs, n, and the size of each job, and then the number of machines that we are going to use, and then the positive integer k, which defines when the unavailability will be added, and then the duration of unavailability period u. So that is the scheduling variant. Coming to the bin packing variant, we have that we have n items we need to pack, and each item has a size si, and then we have infinite number of available bins, and the size of a bin is 1. So we can scale down the due date, and it becomes 1. Then we have a positive integer k, which defines when an ideal uh, unavailability period is added. So the unavailability period, when it comes to the bin packing variant, it becomes something called as an idle item, because we essentially do not have idle time in bins. So after packing k items, we need to add an idle item, and the size of the idle item will be equal to u. The objective function for the scheduling variant will be to minimize the makespan, And then for the bin packing variant, it would be to minimize the number of bins. So this problem generalizes some other problems. So I'll explain the scheduling variant first. So when the number of when k is at least 10, that is we essentially the unavailability requirement is redundant. We can pack any items however we want, and there are no issues. And so this becomes the makespan minimization on identical machines. When the period of unavailability is very large, for example, greater than the size of the total item size, then it becomes adding an idle item becomes infeasible. It doesn't lead to an optimal solution. And and when we have the number of jobs is less than m times k, it means that we can schedule m jobs on k jobs on m machines, and this is feasible. And so there is no need to add an idle time. Then if you try to solve this problem, this is equivalent to the cardinality constraint scheduling problem, where we have an upper limit on the number of jobs on each machine. So that is for the scheduling variant. For the bin packing variant, when k is at least n, similar to before, the unavailability requirement becomes redundant. So it basically becomes bin packing problem, the standard bin packing problem. When u is equal to 1, we can no longer have an idle item in a bin. So when u is equal to 1, adding an idle item to a bin becomes infeasible. So we can only have at most k items in a bin. That means that this is the cardinality constraint bin packing problem. So that's a general explanation of the problem. I'll try to get in the scheme. So the first thing is like instead of the periods of unavailability, we have idle items of size u. So after packing k items in the input instance, we need to add an idle item of size u. And then this repeats. Then a feasible solution is a feasible solution to this bin packing problem is a packing of the bin such that the unavailability requirement is satisfied and the total size of items in the bin is at most 1. Now this total size of the items will include the idle item as well as the items in the input instance. And the objective is to find a feasible solution that minimizes the number of bins. So an upper bound on the idle items in a bin is at most 1 over u, the rounded down. So this gives us basically how many idle items could be packed in a bin. And rounding down is just to get an integer value. And then the upper bound can be obtained by saying that for each idle item that is packed into a bin, we can have k items from the input instance, and we can add one more set of k items without adding an idle time. So this becomes the upper bound. So for each idle item, we have k items before that, and then we have like one set of k items after the last idle item, and that becomes the upper bound on the total number of items in a bin. Based on this upper bound, we consider two cases. It's basically a technique that's very commonly used in cardinality constraint bin packing. So we divide the upper bound into two cases. So where we have k is at most 1 over epsilon squared. This means that the number of items in the bin is upper bounded by 1 over epsilon squared. And in the second case, k is strictly greater than 1 over epsilon squared. That is the hard case. And the first one is the easy case. So coming to the first case, this is the easy case. So the number of items in a bin is at most a constant. Now a constant here means a constant when epsilon is fixed. So number of items in a bin is at most 1 over epsilon squared. Now for the overview, so we create the schemes independently for these two cases, and it depends on the instance. So when the instance belongs to case 1, the scheme will choose the scheme for the case 1. And when the instance belongs to the case 2, it will choose the scheme for the case 2. Now for the scheme for the case 1, the overview is that first we again round the input. So it's basically adding structure to the input as I explained before to get a more ordered input instance. And then we approximately solve a configuration linear program. I'll explain all of those terms. And then we convert the, the fractional result that we obtain into a packing. So the first step is to round the instance. So here we apply linear grouping and rounding to the entire input instance. Instead of like restricting the instance, we apply it to the entire input instance. The number of classes is fixed to be 1 over epsilon cube, and the classes are denoted by Ti. Now the linear grouping basically means we partition the input instance into like different classes based on these two criteria. So the first criteria is that the cardinality of so the after linear grouping, what we need to have is that the items of the first class should be the largest items in the input instance, and the cardinality of that class will be equal to epsilon cube times the total number of items rounded up. And the last class will be the set of smallest items in the input instance, and the cardinality of that would be epsilon cube times the set of number of items in the instance rounded down. And this will give us a unique classification of items into input unique classification of the input instance into classes. Once we have the classes, we round up the sum of the classes. So the items in the classes 2 to 1 over epsilon cube are rounded up, and the items in the class 1 are not rounded. So what we mean by rounding is that each item in the class 2 to 1 over epsilon cube will be rounded up to a size equal to the largest item size in that class. So for the considering class 2, if we have like a 1 epsilon cube cardinality of T items rounded up, and then all of these items will find the maximum item size in that class, and all the items in that class would be rounded up to that value.
So one question. So
Yes.
here you are rounding up the even the small items. I mean, here you are assuming that number of items is less than 1 by epsilon cube or something, but there can be very small items as well. So how do you deal with very small items?
No, we are not assuming that the number of items is less than 1 over epsilon cube. It can
No,
be
yeah,
great.
capital K is less than something you showed, right? Capital K
yes.
is less than. So that,
but that is for a
just,
bin.
Yeah, that is for a bin. Yeah. So we are assuming that in a bin, there is only a constant number of items, but the items can be very small in size. So when you are doing the rounding, how are you doing the rounding? Because if I mean, if you just round to the geometric next, let's say multiple of 1 by 2 to the power I or something, then there are too many classes.
No, the rounding is based on the items in that group. So if we have, for example, let's say that the small items are in this last class, the 1 over epsilon cube class, then all of these items would be of almost the same size because we are sorted in the non-increasing order of size. And the rounding is such that all the items sizes are increased to the largest item size in that class. So each item.
But my question is like linear grouping. When you do in traditional linear grouping, we only do it for big items. For small items, we don't do linear grouping.
Okay.
I mean the traditional.
Yeah, but in this case we can do it because essentially we have a upper bound on the number of items in a bin, so it doesn't lead to a violation of the linear grouping results.
No, but you are doing in the instance, not in the particular bin.
Not for the large items. Yes.
Okay, let's go. I mean, I think probably it'll be clear after something. Yeah, thank you.
Oh, okay. I'll try to explain again a bit. So here we are rounding the entire input instance, and for each, so essentially we sort the item set into like the entire input instance in the non-increasing order of size, and then we divide them into classes. And so the items in each class is not rounded up to a very large value. Each item size is rounded up to a value that is very close to it. So it doesn't lead to an explosion in the items. Like a small item cannot become a large item. And then what we do is we take the first class and then we pack it separately. So the number of bins required to pack the items of the first class is at most epsilon times opt plus a constant. And we prove this, and then it's very easy to prove that. And then what we do is the remaining instance without the first class is called the rounded instance. And then because of the rounding, we have at most a constant number of item sizes in the rounded instance. And then the rounded instance will be packed using a linear program. So next we show that the cost of the optimal solution of the rounded instance is at most opt. So in order to see this, essentially we can consider a solution, consider the optimal solution of the original problem. And then what we do is we increase the sizes of all the items to the rounded size. So only the items of the first class won't be changed. All the items in the other classes would be changed. So essentially, we'll
So
have infeasible bins.
can you again explain the rounding scheme? So if you have n items, how
Yes.
do you exactly do the rounding? You sort the items according to the size, and then how do you find like how do you define these groups? 1/epsilon cube groups?
Yes, based on these two criteria, essentially it's equivalent to like solving a simultaneous equation. So we have like groups of this size and then groups of the lower size,
No,
and then
so
we can
this
like
the size of T, cardinality of T is what? T is the
the
number of
input in.
items.
Yes,
Yeah. So it is like n. So each group contains a lot of items, like order n items
yes,
roughly. Okay.
epsilon
And
cube n rounded up, and we have essentially two groups. If the number of items is greater than 1 over epsilon cube, we'll have like two groups. One group would be having size epsilon cube n rounded up, and then we'll have another group that is epsilon cube n rounded down.
I see.
And then we can just use simultaneous equations and we can get a
I
solution.
see. Now I get it. So you are saying that okay, we can still use linear grouping, but only for the first group we have to say that okay, this epsilon cube n items can be still packed into small number of bits. Then it is fine. Okay.
Yes,
Now I
yes, yes.
understand. Okay.
So the number of bins would be essentially epsilon times the number of bins in the optimal solution.
Yeah, now it's fine. Thanks.
Now we have, so after the rounding, we have a constant number of item sizes. So we'll have at most 1 over epsilon cube distinct item sizes in the rounded instance. The rounded instance is then packed using a configuration linear program. So now back to the proof. So here we start with the optimal packing. Then we increase the sizes of the items to be that of the rounded size. So now then it results in infeasible bins. So some bins can have size, like some bins can have items whose size is more than 1. And then what we do is we remove the items of the first class out of the packing. So now we have like places to move around items. Now, once the first class is removed, we can use those positions to pack the items of the second class. And from the properties of this linear grouping, like this property, and like combining these two properties, we can say that we have enough positions to pack the items of the class 2 for after removing the class 1. So we remove the class 1, we put the rounded items of class 2 into the positions of class 1, and we have enough card positions, and the size also requirement is satisfied. And then we do this like sequentially for the other classes as well. So the items of class 2 is moved into the positions of class 1, 3 into
Okay,
positions
sorry.
of class 2. Yeah.
Can you like so what are we trying to prove here? We are trying to prove this lemma, is it? The cost of
Yes.
optimal packing of the rounded instances at most opt. So yeah, you're considering one optimal bin, one bin in the optimal packing, and you're
No,
looking
we're
at
considering the entire optimal packing.
yeah, okay. Okay, can you like explain it once again, like the proof of the
Okay,
lemma?
sure. Yeah, I'll try to write it. Let's see if it works. So let's say that we have like n bins. And then what we have is we can like for each of these bins and each of all the packings, we modify the size to be that of the rounded instance. So essentially we replace the original input instance by the rounded instance. Now we have bins that contain rounded items. Are you okay with that?
Yeah, that's okay. Yes.
Okay. The next step is to like remove the items of the class 1. So the rounded instance doesn't have the items of class 1. So we remove those out. So now we have positions free. We have like free positions in bins.
Sure.
Okay. And then what we do is we can move the items of class 2, the rounded items of class 2, into the positions of items of class 1.
Okay.
because we have the condition that the number of items of class 1 is at least that of number of items in class 2, and the largest item size of class 2 is at most the smallest item of class 1. So we can move around these items.
I see. So okay, so you will be like moving items from one bin to another bin also.
Yes.
So class 2 items, like class 2 items in the first bin may move to the class 2 items in the second bin also.
Yes.
Class
And
1
then
items.
we can yes, and then we can move from the items of the class 3 into class 2, and we can do that like for all the classes.
Sure. Okay, fine.
So we are not using up more bins. So it becomes the number of bins remains at most that of opt. So that is the proof of the rounding. So this is just to go back to the technique. So here we have this input instance I, and then we have this input instance I, and then this is now changed to a input instance I, and now this is changed to a new instance. This is the rounded instance. The I hash is now equivalent to our rounded instance. And now we have this in the rounded instance, we have at most a constant number of item sizes. Constant once epsilon is fixed. And because of this property of the rounded instance, we can solve them much more easier than the original input instance. And we use a linear program to solve it. So then we'll get an optimal solution for that rounded instance. And once we have that, the optimal solution is translated back into the solution for the original instance. So to do that, we use configurations. So basically, configurations encode the information of how a bin is packed. It essentially gives us the information of how a bin is packed. So in this case, we have at most 1 over epsilon cube different item sizes. And then we can have a configuration, which is essentially a vector of length 1 over epsilon cube. And each component can give us the number of items of that size. So this information is then used into a linear program to get the packing of the final packing of how all the bins in the solution would be packed. Now the components of configuration are the number of items of each rounded size, and then the number of idle items. So the idle items is essentially dependent on the number of items in the rounded size, and it can be removed. Then we have an exponential number of configurations because so a number of items in each bin is at most 1 over epsilon squared, and we have 1 over epsilon cube different components. So we have 1 over epsilon squared raised to 1 over epsilon cube number of configurations. So that's an exponential number of configurations, exponentially 1 over epsilon. And then if you we can now use an integer program to get a scheme, but then the result would be an AP task, not an AFP task. So in order to get an AFP task, we are using a linear program, and then we round the solution of the linear program to get the final packing. So this is the linear program. The decision variables are the configuration counters for each configuration. So we have exponential in 1 over epsilon number of configurations, number of configurations, and and an equal number of decision variables. So we are trying to minimize the number of bins. So that is the objective function. So XC counts the number of bins that are packed using configuration C. So we are trying to minimize the total number of bins. And then the configurations are chosen in such a way that this alpha CC is the component of a configuration. So alpha CC represents the configuration C, and it defines the number of items of size C, small c, packed into a bin that is assigned this configuration. So alpha CC, so this constraint essentially enables us to choose configurations in such a way that we have enough positions to pack all the rounded items, and that's why we use this constraint. And the last constraint is non-negativity constraints. So now we have a polynomial number of constraints, polynomial in 1 over epsilon, because the number of distinct item sizes, the capital C, is at most 1 over epsilon cube. And then we have exponential number of variables. Now this can be solved in polynomial time by using column generation technique. Before that, sorry, I forgot the slide. So we show that the cost of the optimal solution of the, this should be a linear program. The cost of the optimal solution of the linear program is at most the cost of the optimal solution of the rounded instance. And then when we solve this configuration linear program using a column technique called the column generation technique, it's a little complicated. So I'm not like going into it much detail. So essentially what we can do is if we have a linear program in that has exponential number of variables, but a polynomial number of constraints, we can create the dual of that and then solve the dual, and then we can get a polynomial number reduced primal program with polynomial number of variables as well as a polynomial number of constraints, and then this can be solved in polynomial time. So now we can solve this configuration linear program. And then once we have
the LP once again.
Yes.
Okay, what is capital Z?
It's the number of distinct item sizes in the rounded instance.
Is that not a constant?
It's 1 over epsilon cube at most.
Like, yeah, I mean, like in terms of epsilon, it's constant, no?
Yes, it's the number of classes essentially.
So
at most number of classes.
So the entire like this linear program that you have is of constant size, where the constant depends on 1 by epsilon.
But since we are aiming for an AFP task, it has to be the time complexity has to be a polynomial in both
AFP task. Okay, fine.
Yes.
Yeah, sure.
So that's why if we can directly solve this using an integer program and get an AP task, but that's already done. So we are going for an AFP task. So the AFP task requires the we need to solve. It requires that this configuration linear program should be solved in time polynomial in both the input encoding length and 1 over epsilon. So that's why we are going with the linear program.
Okay.
So then we approximate the linear program using the column generation technique. And now we have, we get a basic solution polynomial time. And now once we have this fractional solution, we can round up the fractional solution just by rounding up each non-zero component. And then what we do is now we have integer number of configurations after rounding up. Then we show that the increase in this number of bins after rounding up is at most 1 over epsilon cube minus 1. So this would be the additive in the approximation ratio, in the asymptotic approximation ratio. And then what we show is that, increase in the const is at most number of consts. Then the basic proof of this lemma uses the fact that the number of components in a basic feasible solution is at most a number of constraints. So here the number of constraints is at most capital Z, and that is at most 1 over epsilon cube. So we can use that here.
So basically, what you show is that the number of non-zero configurations is like a polynomial in 1 by epsilon or something.
Number of
is it like number of non-zero? I mean, so number of configurations which are actually packed. So that is like a polynomial in 1 by epsilon. Okay. Yeah.
And so yes. So now the rounding, it does not increase the cost by 2 months. Essentially, that is what the lemma is. And then what we show is that once we have this rounded solution, we can assign bins to configurations based on this integer solution that we have now. And then once we have configurations assigned to bins, it's very easy to pack the items. For each bin, now we have the number of items that can go into the bin, and we can pack the items to bins basically based on that. For each bin, we can pack based on the configurations. It's very easy. The next step is very easy. And that ends the first case. And now we go to the more difficult case when k is greater than 1 over epsilon squared. So in this case, we do not have an upper bound on the number of items in a bin. And then what we have is that so it becomes harder. So we need to like make some we need to introduce some structure into the solution in order to somehow capture this more complicated scenario.
So just a question, in the previous case, where did you use this U explicitly? Did you use anywhere the
we are not
U?
using U. So essentially here, when we define configurations, I skipped that
it's
part.
Implicitly there.
Yes, we have feasible configurations defined. So a feasible configuration will have that the total item size, including the number of items, would be at most 1. So essentially, we use only feasible configurations to pack feasible configurations in the linear program. So that gives us that the final solution after the packing would also be having the that will also satisfy the unavailability requirement.
So in the second case, intuitively it means U is small when you have large K value.
Yes.
Okay.
Yes, that is one of the nice properties that I was going to explain.
Okay,
so
and
here
the value of U, it may depend on the number of the size of the input instance also. Is it like otherwise if U is a constant, then I think K will always
U depends on the input.
Yeah, so it can be like 1 by n, where n is the number of items.
Yes, and it can also be 1 as well.
Okay, sure.
Yeah. So we do not have an upper bound on the number of items in this case. And then the overview is that essentially it's the first step to all the schemes. We linear group and round the input instance. In this case, we only linear group and round the large items. And then we reformulate the problem to a different problem that allows us to make use of some structure in the reformulated problem. And then we solve a linear program as before. And then we use the when we approximate the linear program, like in the last case, and we convert that linear program into a fractional, round up the linear solution, fractional solution into an integer solution, and then we pack based on that. So the first step is the rounding. So what we do is first we classify the items into small and large. Small if the size is at most epsilon, and large if it's greater than epsilon. And then we apply linear grouping and rounding only to the large items. So here, similar to before, we have these two criteria which define the linear grouping. So the first class of large items would be the largest large items, such that the cardinality of that class would be equal to epsilon cube times the number of large items rounded up. And then once we do that, once all this grouping is done, we have at most epsilon cube, 1 over epsilon cube classes. Then the items of classes other than 1 is rounded up as before. So each now we to explain the rounding a bit more, we consider each class. For each class, what we do is we find the largest item size in that class, and then we round up the item sizes of all the items in that class to this maximum size. And then that finishes the rounding of the input instance. So now we have only touched large items. The small items remain the same. And then we take the largest items of the first class and we pack them separately. Again, we show that the number of extra bins that this consumes, it's at most epsilon times opt plus a constant. And then the remaining large items, the items other than that of the class 1 are packed using the linear program. And this instance is called the rounded instance. So the rounded instance will contain small items that are not modified, whose size is not modified. And it will contain the large items from class 2 to 1 over epsilon cube, whose size is modified. And then after rounding, we have that the number of the distinct item sizes of large items is at most a constant when epsilon is fixed. Again, so as before, we show that the cost of the optimal solution of the rounded instance is at most the number of bins used in the optimal solution. So as before, we consider the optimal solution. We do not touch or modify the small items. Only the large items are modified. So we increase the size of the large items to be that of the size in the rounded instance. and then we remove the items or large items of class 1 from the packing, and then we move the items as before, and we can get a feasible packing. So then this shows us that we are not using more bins to pack the rounded instance. And then we reformulate the problem. So here, this is a little bit more complicated. So I'll go a little slow. So the reformulation allows us to pack the small items. And first, what we do is we need to have an item set that is sorted based on the size. So we are sorting the item set in non-increasing order of size. And then we can sort this because we can rearrange items in a bin. It is feasible to do so. We can move around the items inside a bin, and it still remains feasible. And what we do is we introduce these two terms called early and late for items. So an item is early if it is among the first k or epsilon items in a bin or in an item set, and it is late otherwise. So if we see for the first k or epsilon cube items in an item set in a bin, and only these items are called early, and the remaining items after that are late. So I'll just explain this reformulation a bit more. So this reformulation is based on the relaxation of an original problem. So essentially, what we can do is, if we have a like ideal item like associated with late items, we can split that ideal item among the k late items. We can and then increase the size of these late items, and we can essentially, it's a relaxed form of this problem. So to explain it further, consider this top schedule or a packing. What we have is that these items up to this like dots are the early items, and all of these primed items are the late items. So what we do is we keep the early items as they are. We do not modify their size, but for late items, we modify the size. So for late items, what we do is the size of each late item is increased by u by k. So the ideal item that is added after k items would be split and given to each late item. So this reformulation increases the item size, but we show that it's possible to somehow alleviate that problem. So this is the reformulation. If anybody has a doubt, please ask.
So after this reformulation, you essentially don't need to consider the ideal items when packing. Is that the
yes, for the late in case of
reformulation?
yes, for the late items we can just ignore the ideal items.
Okay, fine.
And then we have, like, since the number of the early items are at most k over epsilon, we have at most 1 over epsilon early items. Early ideal items corresponding
Ideal
to the
items.
early.
Okay.
Yes.
Okay, fine.
So after this reformulation is done, the unavailability requirement is modified to be satisfied by only the early items, and then the size of the early items remain the same, and as in the rounded instance, while the size of the late items are increased by u by k. And the large items are early because in each bin, since the size of a large item is at least epsilon, we can only have at most 1 over epsilon large items. So all the large items would be early, and only small items could be late. So then we show that this is the nice property that that was mentioned before. So if there exists a late item in a bin, then there exists a set of k consecutive early items such that the total size of these early items together with the ideal item is at most epsilon. This is easy to see because if we have at most 1 over epsilon such consecutive sets of early items, and if each of those are greater than epsilon, we cannot have a large item, we cannot have a late item. So there should exist at least one such set. So we use that and show that the cost of the optimal solution of the reformulated problem is at most 1 over epsilon times the cost of the optimal solution of the original problem plus an additive constant. So essentially, we convert a feasible packing of the original problem to a feasible packing of the reformulation problem by modifying the size. And then we move out a set of these k consecutive early items from a bin. And then that makes it feasible. And the next point is the configurations for this case. So again, configuration encodes the information of how a bin is packed. In this case, how the reformulated solution looks like. So this is more complicated and we require more components. So we have the number of large items. We have a component equal to the number of distinct item sizes of large items. That is at most 1 over epsilon cube. And then we have a number of early items that are in a bin. Now this is say encoded as integer multiple of k. So this becomes like at most. I'll skip that. Sorry. So I'll try explain again. So the configuration vector will have a component equal number of components equal to that of the distinct item sizes of the large items after rounding. Then it will have a component that stores the number of early items, and then it will have a component that stores the total size of late items. Now, since the size of a large item is at least epsilon, the number of large items would be at most 1 over epsilon. And then the number of since we are saving this number of early items as integer multiple of k, this will also be a function. We can write this as a function of 1 over epsilon. And similarly, since we are saving the total item size of the late items as a multiple of k, we can also write this as a function of 1 over epsilon. So all of these configurations will now be exponential in 1 over epsilon. I mean, the total number of configurations would be exponential in 1 over epsilon. And then we have this configuration linear program. So in this configuration linear program, we have these following decision variables. So we have a configuration counter for each of those configurations. And then we have an assignment variable for the small items. The small items can be assigned as early as well as late. So we have two variables corresponding to those. So assignment variables for small items as an early item, and assignment variables for small item as a late item. So again, we have an exponential number of decision variables, but the number of constraints would be polynomial. I'm not showing the linear program here because it's way too complicated. So next, then we show that the optimal solution of the configuration linear program is at most opt. And similar to before, we use since we have a exponential number of variables, exponentially in 1 over epsilon number of variables, we use column generation technique and polynomial number of constraints. Excuse me. So we have exponential number of decision variables and polynomial number of constraints. And then such linear program can be solved using in polynomial. Such linear program can be solved in polynomial time using the column generation technique. And then we approximately solve this column generation technique, approximately solve this configuration linear program. And once we have this approximate solution, we can round up the solution. And this rounding up does not increase the cost too much. It's only a constant once epsilon is fixed. And once we have this, sorry, I can't hear you.
Hello, can you hear me?
Yes.
I was asking that, so here you are introducing a variable for every small item, like two variables for every small item, whether it is assigned as an early item or a late item.
Yes.
So basically now the size of the linear program also depends on like n. So like in the previous case, it was a constant in terms of epsilon, but here it depends on n, right?
Yes.
But that's not a problem.
No, that's not an issue. Yes, yeah, because essentially what we do is we have this primal problem with like exponential number of constraints, exponential number of variables, and polynomial number of constraints. So we write we write a dual of that. So we'll have like a polynomial number of variables and exponential number of constraints. And then we use the column generation technique uses an ellipsoidal algorithm to reduce this.
Okay.
And so the resulting dual program after the reduction would be having a polynomial number of variables as well as a polynomial number of constraints.
Okay.
And then we can like translate it back to a primal and solve the primals.
Yeah. Okay.
Okay. So we can solve that linear program. And then once we have that solution, we can round up the fractional solution. And then once we have the rounded up solution, we can like assign the configurations to the bins. Now we can pack large items easily because we have the number of large items exactly defined. And now since we rounded up, we have more space for large items. So some items, some positions in some bins for large items could be empty. Now those small items, since we have a fractional solution, again, it becomes very hard to pack them. And it requires more complicated approach, which I'm not explaining now, but I can explain later if you would like. And that gives us the packing of the scheme. That gives us the output. And we are done. Thank you.
Yeah, thanks for the talk. Questions?
Yes, questions, please.
So one question I have is, you are using same U for all bins. Let's say in the scheduling version, makespan minimization. If I have different bins and I use different U values for them, depending on the bin.
No, the U is same. It defines
no, right now you're using same U, but let's say I use another variant where depending on the machine, the U can be different. There are some M number of machine and you're trying to minimize the makespan, but the U can be different in different machines. Do you think the techniques can be extended to that case?
So essentially, only the U is different for each machine, and the item sizes remain the same. I mean, is it not? Is a case not like unrelated? Is it case like, are the speeds? Is it a related machines case, or is it something else?
It's a same identical machine kind of a case, but now it's not clear. Maybe I was saying that this U value is only different. Other things are same. So it's like identical machine. Only the I was trying to understand what is the next general problem that you can solve using the technique. So whether before going to related setting or going to the unrelated setting, it's harder. So maybe the intermediate step could be it's identical machines almost, except the value of U can be different in different machines. If that is the case, it's still the techniques will still extend in that case.
That is a good question. Sorry, I don't have an answer. I need to think about it.
Sure. And in general, for unrelated machines, etc., what can you do? Like some approximation, etc., is it possible to get
for this problem?
Yeah.
No. Again, we haven't like delved into that yet. Sorry. Yeah. I'll stop my sharing.
Sure. Yeah. Thank you.
And can you give a brief idea of how do you assign the small items at the end? Like what sort of, like it's a greedy thing or something else?
Okay, so we have fractional solutions for the small items. So essentially, after we get the fractional solution for the linear program, we only round the configuration counters up, and the fractional variables of the small items remain as is. And then what we do is we assign these small items to the bins based on this fractional solution, and then we get essentially an assignment variable of small items to bins, and then we write a feasibility linear program for that case only for the small items, and then we show that the number of fractional small items in a bin is at most 1 over epsilon cube. It's a function of 1 over epsilon cube. And then what we do is, since we have small items, since the items are small, all of these small items is size at most epsilon. So we can pack them in a bin, and the number of these small items would be at most 1 over epsilon, and we won't need an ideal item. And it's very easy to like pack those fractional small items separately.
Okay.
I hope you're able to understand.
Again write a different linear program for the small items just to pack the small item.
Yes. So it's just a feasibility linear program. And then we should say that the number of fractional components is at most a function of 1 over epsilon. And that again adds to the asymptotic approximation ratio.
Okay. Yeah. Okay.
Any other questions?
Yeah, if there are like more questions. Yeah, if there are no more questions, then let's thank the speaker. Yeah, thanks, Jaykrishnan, for giving the talk.
Yeah,
Thank you for inviting. Yes. I hope you were able to understand.
Yeah, it was very nice talk. I could understand.
Yeah.